Let's take a look here at skills check number 1. Remember that the purpose of the skills check is to cover some prerequisite material, things you would have learned in an algebra class, pre-calculus, and Calc 1 that we're really going to need in order to be successful throughout the first unit in our first exam. Now, you can see here that I've broken this down into 5 different categories of questions. And these styles of questions are things that are possible to be asked on quiz number 1, in addition to some of our new content. But let's take a look here quickly at the categories, and then I'll kind of work through a couple examples off of each of these. If I take a look at the first category, it's identifying bounded regions. Category number 2, finding points of intersection between curves. Number 3 and number 4 deal with, can I evaluate integrals, some without substitutions and some with substitutions. And number 5 down here is solving literal equations. Again, all of these are going to be skills that we should already possess, but of course, you may forget some things from time to time, or maybe a little bit rusty. So we're going to go ahead and take a look at each one of these different categories by going through just a couple of these questions. Well, let's start looking then at number 1. I want to try to identify bounded regions throughout our first chapter. It's going to be a very, very important idea. So I should be able to go ahead and answer a question like what I see here in maybe, let's say, number 1A. Okay, so in number 1A, I want to shade the region that is bounded by the following curves. So you can see here I have an h of x, which is my natural log. I have an x equals 1 and a y equals 2. And I want to go ahead and sketch what each of these is going to look like. Well, if I was to go ahead and try to complete this maybe over here on the side, I could definitely see that for 1A, if I want to sketch a natural log graph, I might recall that my natural log graph looks something kind of like this. Again, it's going to be crossing over my x-axis at a value of 1. It's important that I understand what this graph looks like, as it'll be one that'll come up very frequently this semester. I can also see here I have a line x equals 1. Remember, that's a line where, well, the x-coordinate is always 1 for all points on that line. So that's going to be a line that goes like this and moves up this way vertically. I'm also then going to have y equals 2 as a nice horizontal line. And so let's just say, for the sake of argument, that that horizontal line goes like this. That's up at y coordinate 2. Well, what I'm looking for is a region that I can imagine as being kind of bounded by these different curves. Or sometimes you could imagine these curves as acting like fences. And I want to find the yard that is fenced in by these particular curves. And what I might be able to see here is like this space right here kind of in yellow seems to be kind of the region that I would be working with. And so if I was able to produce something like this on quiz number 1 for an associated question of this type, I would be able to earn full credit. So we might be able to see that when completing questions in this first category, it's going to be really important to know the shapes of many different types of graphs, including things like our sine, cosine, tangent graphs, natural log of x, e to the x. All of these are very, very important. And if you take a look underneath the Exam 1 materials, you'll see that I've put together a little sheet there of graphs to know that I think are very important for us to be able to just know offhand in this semester. And if we don't have those down, we're going to often find that we're going to be a little bit sluggish or slow to kind of start different problems because we won't have a good intuitive picture about what a lot of these curves look like. We'll take a look then at part C here for number 1, just as for a point of contrast, because here we have a very, very different sort of a function. Here we have an x is equal to a negative y squared and x equals negative 4. Now you may or may not have spent a lot of time dealing with equations that start with this kind of x equals format. But if that's a bit overwhelming for you, try to break it down by just thinking about this as something that you could sketch after plotting a bunch of points. So I'll start by setting up a table of values. Of course, here it might be easier to first go ahead and pick values of y. So maybe I'll pick a value of y like a -1, a 0, and a 1. And once I have those, I can easily go ahead and calculate the associated x values that end up going with this. So you'll see here I can create a whole bunch of these values, and then if I wanted to go and create a picture of what this actually looks like, I'll see that obviously 0, 0 is a point on here, -1, -1, and -1, +1. And so some of you may have already guessed that this is going to be something that looks like kind of a sideways parabola-like shape. Now, of course, if I also want to sketch something like an x equals a -4, let's just say for the sake of argument that happens somewhere out here, this being x equals -4, if these lines continue on a bit further, like this, then of course I again can easily see the region that I'm going to be covering. It's going to be this space. So sometimes when I get this kind of an x equals function, it can be a bit intimidating, but if I plot points, it should be easy to go ahead and determine that shape rather quickly. You may have also guessed that this was a sideways parabola because it was still one variable equaling the other variable squared, and so it has that quadratic type shape. And of course, since this is starting with a negative coefficient, that means it's going to be opening towards negative x values, which is exactly what we see here in the picture. Well, now I'm going to go ahead and move on to the second set of questions, finding points of intersection. And this here should hopefully be fairly simplistic. Let's take a look at an example like 2a. Very straightforward. Find the points of intersection between these two curves. Notice here that I am specifically asking for points of intersection, so I want x and y coordinates. So if I was going to go ahead and do a question like this, so tackling 2a, I know that if I want two curves to be intersecting, then that would mean that wherever these curves are actually located in a picture, they have a point where they share the same x and y value. So of course, if I want these things to have the same y coordinate, then I know that I could just set them equal to each other. I would be curious what x would allow both of these things to produce the same y, that is, to match each other. And of course, once I have this, I'm down to actually just working with a very, very simple quadratic equation. Now here, I can see that I can probably factor on the one side, since this is set equal to 0. And it looks like this might factor into an x minus a 3 with an x plus 2. Of course, then I know that means one of these factors must be equal to 0 for the product to be 0. So either I'm going to get x is equal to 3 or x is equal to -2. Now, again, I haven't quite answered the question because I need to kind of turn each of these into a specific point. But it's pretty easy to see here that if x is equal to the value of 3, then finding the value of y can be done by plugging 3 into the left equation or by plugging 3 into the right equation. It doesn't matter which because they're supposed to produce the same y. I'll plug it into the linear one just because it seems a bit easier maybe to work with. Notice if I plug 3 in, I do get the result of 12. I can also see that if I take this value of -2 and I plug that in, I'm going to get -4 plus 6, and I'm going to get 2. So these would ultimately be 2 points of intersection. Now, you might be dealing with different sorts of functions here. As I see here in parts B and C, I could have things with logarithms, I could have things with radicals, you could expect things with trig functions or exponentials, I mean, anything like this, but the approach is exactly going to be the same. So hopefully that gives you an idea of how we would answer something like questions of the second type. Now I'm going to go ahead and take a look actually at questions from type number 5, solving literal equations. So if I was taking a look at number 5, you'll see here that all these questions are going to be giving us a function that is in this y equals bunch of stuff with x form, and they're going to want us to solve the equation to say x equals. That is, x equals a bunch of stuff with y. Now, in a lot of cases, this is very simple and straightforward. In fact, for part A, this almost probably feels like a joke. This is stuff we might have been doing since an algebra class. But I'm going to go ahead and take a look here really quickly at 5C, just so we can maybe quickly recall how we deal with things like logarithms and solving for the value of x that's listed here. Okay, so you might recall that if I'm interested in, I guess, quote-unquote, removing this natural log, what I can do is I can take both sides and make them exponents of an e. And you might recall that when I do something like e to a natural log, those are inverse functions, and they essentially, I hate using this language, but they cancel out, and they ultimately leave us with this x plus 2. So I can go ahead and make both sides powers of e to remove the natural log. Well, of course, once I'm here, it's pretty easy to see that if I just subtract 2 from both sides, I have exactly what I need. I have x equals a bunch of stuff with y. All the questions of type number 5 are going to be similar to something like this. You can see here that I have a fifth root, here I have a fraction, but I need to make sure that I have x equal to only stuff that contains y. I can't have x's that also remain on that side, or I haven't fully solved for x.